systems of units are based upon fundamental quantities. Fundamental quantities are definitions of various physical or chemical events or properties that you are trying to measure. In the essence of systems of units, we've divided these fundamental quantities into length, weight, time. You have others that are volumes, like gallons, lumens, auditory sounds. Those are pretty much fundamental, because what we need is a description of what you're trying to measure. And fundamentally, there's an English system and a MKS system, or SI system, Standard International. Now, for anything to make sense in a description, three things are required. Well, for unit system. A definition of what you're trying to measure, define, and you need a standard of measurement, and a method of comparison of the measurements. Comparison of measurements. So, in trying to keep everything on one page here, in the English system, we all recognize the 1 foot and 1 pound and time 1 second, or one just simply S, like that. But in the metric system, it is an MKS system. In study of science, frequently the community will use abbreviations for whatever the standards are: CGS, centimeter gram seconds, or MKS, meter kilogram seconds, as the first letter in each of the systems. And these are the standards. So M is a meter, and kilogram, that's a multiple of the gram. But the gram is so small, it's about, if you take a penny and cut it in half, that's about a gram. And 1 second for the standard of time. Now, in the nature of comparison, we use prefixes as multiples or fragments of this system. So what I want you to do, these will be prefix designations. And I think you know where I'm going, centai and mega and those kind of terminologies. Well, draw a vertical line, and right in the middle you put your standards, and that's of course your meter, kilogram, and seconds, or mass. But we have to take the gram value to use the prefixes, because you have value prefixes that are larger than the standard and prefixes that make fractions out of the standards. And so what we typically do is times 10 or times 100 times 1,000 times a million times a billion or a trillion, like that. And so if we're talking about 10 units or 10 meters, what we want to do is put a prefix deca onto the meters, or do we want to talk about 10 grams, we use a prefix decagram, or 10-second intervals, call them decaseconds. Now, 100 of each of the standards is hectometers, and that's talking about 100 meters, and then hectograms, 100 grams. And you'll recognize the kilo as 1,000 is 1,000 times whatever the standard is. A kilogram is the standard of the MKS, or the Standard International. You get into the 10 to the 6 is megameters. You're talking about 1 million meters. Megagram, you're talking about 1 million grams, and so forth. Giga, G-I-G-A, refers to a billion of each standard. Gigabytes, as you are probably familiar, in storage of data. And then you go up to terabytes. There's tera is 10 to the 12. Terameters, that's 10 to the 12 a trillion meters. And so we put those on there to emphasize a block of the standards and use them as a comparison to these standards. Then, of course, there are fractions. We can go to 1/10, which is the same thing as 0.10, which is the same thing as 10 to the minus 1 power. And then you have 1/100th, and that's 10 to the minus 2, and 1/1000th, and that's 0.001, or 10 to the minus 3, and we use 10 to the 1 over 10 to the 6, which is 10 to the minus 6. I'm not going to string out a bunch of zeros. And then 1 over 10 to the 9th, that's 10 to the minus 9, and 1 over 10 to the 12th, and that's 10 to the minus 12. Well, the 10 to the minus 1, or 1/10 of a meter, is a small fraction of the meter, as decile. Now notice I use lowercase here, and it's just a habit I've gotten into. If I'm talking about numbers larger than the standard, I always use capital letters. And that's not required. There's no rule that says use it that way. I just do it. And nobody said not to. And decile is smaller, or it's a fraction of the standard, so I use lowercase, and it's just habit over the years. And 1/100th is, of course, centi. Centimeter, as you're familiar with. And 2 centimeters is about an inch, 2.54 to be specific. Milli is 1/1000th. Millimeter is many milligrams. Millisecond, 1/1000th of a second, 1/1000th of a gram, and so forth. Then you have micro. A micrometer is 1/1,000,000th of a meter. Microgram, 1/1,000,000th of a gram, and so forth. And then you have nanogram, nanosecond, 1/1000,000th of a second, and that kind of thing. And then you have picosecond, trillionth of a second. And so those are used quite frequently, and especially in particle physics, where you're talking about nuclear transition in time frames. At any rate, here you're a collection of prefixes that are used extensively, as you're well aware, probably from other courses, in using these prefixes attaching to the standards to indicate fractions or multiples. It's dimensional analysis. Or the process of converting from one dimension into another. And you won't find this in the textbook, but for academic reasons, I divide these dimensional analysis methods into three categories: simple, multiple, and what we call complex conversions. The simple conversion is unit to unit. That's all it is, a single unit to single unit. Meters to centimeters, or meters to inches. Now, multiple conversions are squares and cubes. Uh, 36 square centimeters is how many square feet? Okay, so we're talking about a power of squared or power cubed. And there's a technique that I want to emphasize as we do these, and it's very simple. Complex is a combination of fundamental units, like density is a combination of mass and volume units, where volume is length, width, and height. You can have grams per cubic centimeter. And so you cannot convert a length into a mass number. And it's always, they're separated. And so you have to leave them in that context. And the units, which are, say, grams per cubic centimeter, you have to leave it in that combination, and that's a complex unit in its definition. So these are conversion of complex units. Okay, now I'll take each one of these and work some examples of that and see how they are applied. Okay, let's say you're given the following problem. How many seconds equal 35 years? Okay. So we want to convert that to 35 years into seconds. Well, we need to get rid of years and go to the unit of seconds. So now there's a thing called an identity in setting this up. Now I like to just go how many seconds equal 35 years, and off I go into my dimensional relationships as we put them in, and we call them conversion factors. Now you will have attached to the exam a big collection of conversion factors. Anything that's a constant, like the universal gas laws, something of that nature, speed of light, those kind of things, that'll be posted on that reference sheet. Or what's the relationship between inches and centimeters? Well, those are on the reference sheet. Is how to use them is what you need to learn. So in this case, we know most of the time elements, and we start with an identity. 35 years is equal to 35 years. That's an identity. And some people like to use these square boxes. I like time, sign, and a line, so it's the same thing. Now, this is actually over 1. So we want to get rid of years and go to seconds. Well, I don't know a relationship between directly between years and seconds, but I use days. So I'm going to say there's 365 days in a year. Okay, so years now cancel out, and so I want to get rid of days, so I put it on the denominator side of the ratio. And again, continue until I can get to where I want to be. And I'm just going to go through hours, and then we'll continue. We'll get rid of hours and go to minutes times, and then of course to minutes, and we end up with seconds like that. Now, these are equivalent relationships. Be sure you get the right number with the right unit. Okay, 1 hour is 24 days. Okay, that's so. Be sure you pay attention to where you place your numbers in your conversion problem. So, and of course, 1 hour, 24 hours make a day. I'm going to write it again. 24 hours is in a day, and so our days cancel out, and so hours need to cancel out in minutes. So there's 60 minutes in an hour, so hours drop out, and 60 seconds in a minute, like that. And so everything's canceled except the seconds, and that's the object of the conversion. So it is all over 1, so I'm just going to go 35 times 365 times 24 times 60 times 60, and tag it with seconds. And then we'll do the calculator answer, and then we'll round it to the appropriate sig figs. Now, what numbers do you use in sig figs in a conversion like this? It's the data. Do not use a conversion factor, because that's not of the data stream. The data should be, so we're looking at 2 sig figs here. So whatever the calculator answer is, we want to round that to 2 sig figs. We need to retain the dimension of it if it's a bunch of thousands or something. Okay, so let's run that out. I'm sorry. And we'll use dimensional linear dimensions, which is, of course, as you would. Then there is cubic centimeters, which is a volume number kind of thing. So well, let's say you're given the following problem. How many pounds, excuse me, I'm sorry. That's another one. Okay, how many cubic meters equal 303.075 cubic feet? And you want to convert cubic feet to cubic meters. It's very straightforward. Listen to me carefully, and you'll see what I'm saying as I go through it. Do a simple conversion, and then, in this case, cube the conversion factors, not the data. This is your data. It's already in cube form. You don't need to cube that. So as I go through this, watch what I do in terms of simple conversion. I'll go from feet to meters, and then I will cube all the conversion factors. So starting with the identity, just feet. Now we want to go to cubic feet. I want to start with 3.075 cubic feet. Then I'll put my conversion factors in till I get to the appropriate dimension. So if I'm going, if on a simple conversion from feet to meters, I want to get rid of feet and go to inches. And then I want to get rid of inches and go to centimeters, and then centimeters to meters. Then I'll go back, put parentheses around the conversion factors, and cube them. And that's your multiple conversion. See how simple that is? So you do a simple conversion, which you probably already know how to do, and you did it 1,000 times. All you do is go back now. Don't cube the data. It's already cubed. Only the conversion factors. So they're 12 inches in a foot, 2.54 centimeters in an inch. That's on the conversion sheet. And there are 100 centimeters in a meter. And they will cancel appropriately because that's cubed. That's cubed. Cubic inches, cubic centimeters, cubic. And that will apply, of course, into the parentheses as cubic meters. So your in unit, in problem, or your answers units is meters cubed. When you enter all the numbers in, you have one in the denominator, and then everything else is numerators. So it's 3.075. You don't cube that, but 12 you do. You want that cubed, and you want the 2.54 cubed, and then 1 times 1 times 1 is still 1. And then you have 100 cubed. You could use 10 squared if you know how to deal with that, but I'll just put 100 right there. And the outcome of this is cubic meters. Now, again, simple conversion, then cube the conversion factors. Now, if it's squares, you square the conversion factors. That's what I got. Y'all back me up. You see that? Okay. Pretty straightforward, right? Okay. As you look through here, what do you use for the sig figs? Well, here's your data. So that's 1, 2, 3, 4 sig figs. Okay. Let me turn it back on. I'm sorry. I hadn't done it already. Yeah, it's on. Okay, so I start from left to right because of the decimal, and you go through the zeros, and here's your first sig fig. That's 1, 2, 3, 4. So we'd round to this position right here. Well, 4 is less than 5, obviously, so we'll leave 7 as a 7. And so our appropriate answer is 0.08707 cubic meters based on the data and problem given. Pretty straightforward. So the method is convert one of the dimensions, complete it as a simple or multiple conversion of whatever you're doing. Then go back and convert the other one. Density is probably the simplest one I think of. Density is mass per unit volume for material. Let's say physical property of a given substance. Say we're given density 2.65 times 10 to the 4th grams per cubic centimeter. Convert to pounds per cubic feet. as an example. So, again, you convert each unit by itself into the appropriate unit needed. So we start with our identity, 2.65 times 10 to the fourth grams per cubic centimeter equals 2.65 times 10 to the fourth grams per centimeter cubed. That's a cube, believe it or not. There we go. And so we'll get grams to pounds first because it's one step. I know what that is. So we want to get rid of grams and go to pounds. And it turns out that 1 pound contains 454 grams, and our grams will neatly drop out. And so that one is taken care of. So we need to go to from cubic centimeters to cubic feet. So we want to get rid of, let's see, cubic centimeters is on the denominator side of the ratio. So when we make our entries of the conversion factors, we want the centimeters to be on top in this case so that they will cancel out as a ratio. And centimeters to inches, we'll use that one, and then inches to feet. And then we will enter the numbers and we'll cube them. Like that, just like I'm showing you in the previous example. So it's 2.54 centimeters in an inch. Again, the conversion factors will be posted on the conversion sheet. And we have 12 inches and 1 foot. So now grams is dropped out, and we get rid of centimeters and inches, and so we're left in cubic feet. So those are the only units, pounds and cubic feet. So collecting the numerical values, see 2.65 times 10 to the fourth, 2.54 cubed, and 12 cubed as we go through that version, and you're dividing by 454. And everything is in pounds per cubic foot, if you can read that. If I didn't miss a button, I have, make that look like a pounds. 1,652,855.583 pounds per cubic feet. However, we need to round that to the appropriate number of significant figures relative to the data given. Now, the data given only has 3 sig figs in it. You do not use, of course, the powers of 10 as an indicator for the power sig figs. So 2.65 indicates 3 significant figures, so it would be rounded to that position as 1,650,000 pounds per cubic feet. So you would not put a decimal into this because you would count right to left, and there's your sig figs. From right to left, it'd be only 3 there. And the zeros are not sig figs, but they're there for the dimensional factor. But anyway, I made up the problems as we went along to give you illustrations of each one. Percent, parts per million, ppm, parts per billion. What do those mean? Well, they are concentration terms to begin with. Which refer to a percentage of course, is the symbology, is actually parts per 100. And you can, some people will put pph for an abbreviation for that, parts per hundredweight, which is by definition, parts over 100, and is a decimal fraction if you leave it in pph only. But what happens is people will multiply it by 100 to get it into a percentage number. ppm is parts per million. Which is simply however many parts over 10 to the 6. Okay? That's what it means. And parts per billion is the same thing, except over 10 to the 9th. And as far as definitions go, give you a chance to jot that down. 0.00275%, and it's got a WW. That means it's a weight based on a weight ratio. There are percentages which are based on volume ratio. Sometimes you buy alcohol at the pharmacy that's 30% isopropyl alcohol and water, and so it'd be 30 mils per 100 mils of mix. This kind of thing, and so that's why we put WW, W/W, or V/V. And some of them have W/M, mass. I mean, volume, M, W/V. At any rate, if we're going to convert these to parts per million or parts per billion, you have to know what percentage means in its just intuitive definition. It's parts per hundredweight. So if you had 0.00275%, what does that mean? It means you have 0.00275 mass units, grams. We'll just throw grams in there. It could be tons, it could be pounds, or it could be whatever. But it's 0.00275 grams over 100 grams of mix. Now, a percentage indicates a concentration term. That's an amount of substance per total volume of solution or mixture. So this is a mix when you see a percentage number. It is a part over a total mix. So if you have this arrangement, that is what it means. Now, if you want to go to parts per million, what do? You multiply it by a million. That's all you do. Now you're in parts per million. Or if you want to go to parts per billion, and it'll give you ppb. And this will give you ppm, parts per million, automatically. Now, the same way going from parts per million or parts per billion back to percentage. Interpreting what do I mean by ppm or ppb. You write it down in the same context. Second problem. Let's say you're given a concentration of element in terms of parts per million. So whatever report you get says it's 287 parts per million. Well, for some reason you need it in percentage. How do you get there? Well, you need to be able to write this in parts per million, just like I showed you first, how to write percentages. So it means you have 287 ppm is 287 parts per 10 to the 6 parts mix. If you have a collection of red, white, and blue golf balls, What's the percentage in that mix? That's what we're talking about. And you can express it in parts per million or parts per billion. It's the same idea. You got, in this case, whatever that element is 287 parts per million. How do you get to percentage? Just multiply by 100 and put a percent on it. It's the same way as we got back to the parts per million or parts per billion from a percentage. You write down what a percent means and then times a million or times a billion. And it couldn't get any simpler. But you have to recognize what the definitions of ppm and ppb are to make those conversions. Like that. Of course, there are temperature scales, Fahrenheit, Celsius, and Kelvin, that we need to be aware of. And given a temperature in Celsius, how do you get to Fahrenheit? Given a temperature in Fahrenheit, how do you get to Celsius? And given any of them, Celsius or Fahrenheit, how do you get to Kelvin? What are the relationships? Well, there are three very classic formulas, and I want to show you where two of them come from. If you wish to calculate degrees Fahrenheit from degrees Celsius, is 9/5, whatever the value Celsius is, plus 32. If you're calculating Celsius, it's 5/9, parentheses, degrees Fahrenheit minus 32. Like that. Those are classics. Okay, so if you have to convert from one to the other, you can use those formulas. Now, as far as a Kelvin, notice it does not have the little degree notation on it, but it is the same dimension as far as separation goes as the Celsius. Okay, but to obtain a Kelvin value is degrees Celsius plus 273. So those are your classic formulas for making those conversions. But what I want to show you is the origin of these two, and it's very straightforward. Using what we call the point slope method from your algebra courses, derive the Celsius, Fahrenheit, back and forth conversion formulas. And you're given the freezing point of water and the boiling point of water here and here. There you go. Okay, so if we use the point slope method, we find that it is defined as y minus y prime equal change in y over change in x, x minus x prime. This you should recognize from maybe your algebra course. Well, relating this to this graph, of course, this is x and y. X is going to be your degrees Celsius axis and y your degrees Fahrenheit. So we'll have a degrees Fahrenheit minus Fahrenheit that is a data point out of the 2 points that we're working with, F minus F prime to equal change in degrees Fahrenheit and over change in Celsius onto degrees Celsius minus a degree Celsius prime. And the prime values will be one of the data points here. And I choose the freezing point 0 degrees and the boiling point 100 degrees as my two numbers because it is one of them turns out to be 0, and it makes it a lot easier to substitute and solve the equation. So what this turns out to be is degrees Fahrenheit, okay, and if we use the freezing points here, and well, the boiling point's 100, that'd be 212. Let's see, 0 degrees C, and yeah, is equal to, well, I'm missing something. Anyway, change in Fahrenheit would be 212 minus 32 over 100 minus 0, so that's change in Y over that, and it'd be degrees C minus the C prime, which would be 0. I think that's supposed to be 100 there. Zero, and well, we'll see what it works out to be. At any rate, I think that's supposed to be 100. 0 Fahrenheit minus 212 is equal to, that's 212 minus 32, 180 over 100 degrees C. And so that is 9/5 degrees C. That's got to be 32. That's what it is. I'm taking the second number. That should have been 32, not just 1 and 2. That's right. I don't know why I'm getting it mixed, but anyway, 32. All right, so you take this, and you solve them for the appropriate degrees C. Is 5 over 9 degrees F minus 32. And then if you solve for degrees F, it will be 9/5 degrees C, and move that over, plus 32. So it just kind of shows you, I just pulled the wrong numbers and got confused. Anyway, by substituting into the point slope, you can get the two classic formulas for making the temperature conversions very quickly, like that. Now, the only other one in this collection is, of course, Kelvin, which is degrees C plus 273. You always have to go to Celsius, wherever you are, to get to Kelvin degrees. Okay, that takes care of temperature. Energy, by definition, is the capacity to do work. According to our physics friends, work from physics is defined as a force acting through a distance. And this can be broken down very simply into whatever, from Newton's second law, is mass times acceleration times a distance. Now, if we substitute SI units into this definition of work, we have kilograms for the mass number. Acceleration is meters over seconds squared. That is the units for acceleration, and distance is meters. And this condenses to kilogram meters squared over seconds squared. And so, yes, I want you to recognize this more than anything. Than what it represents is the foundation of a complex unit that was later defined as the joule. So a joule is a unit of energy that's based upon the definition of work: force times the distance, mass times acceleration times distance, so forth. But it gives you units of kilogram meter squared over second squared, which is a very cumbersome, complex unit. Well, the scientific community many years ago, when they were working with the thermodynamics of energy conversions, define this collectively as a joule. And the meaning of this is based upon the definition of work. The other unit is the scientific calorie. And it is given a lowercase symbol. Now, it is not a dietetic or nutritional calorie. Nutritional calorie is 1,000 scientific calories. So to distinguish between the two, 1 calorie by definition, the amount of heat energy needed to raise the temperature of 1.000 gram of pure water by 1 degree Celsius. That is the international definition of a calorie, thermal calorie. Well, to appreciate this in terms of measuring certain energy values, we relate calories and joules in the following relationship. 4.184 joules is equal to 1.000 calories. And so your conversions are either to calories into joules or joules into calories through this relationship. And of course it is posted on the conversion sheet table, and you can use it. Say you're given 65.2 kilojoules, how many calories or kcals, let's go kcals, does that represent? So you use the same conversions that methods that you've been using. We'll go kilojoules to joules, and then joules to calories, and then calories to kcals. So there's 1,000 calories and 4.184 joules in a calorie, 1,000 joules per kilojoule. And so is very straightforward conversion, and would be in 3 sig figs based on the data given. Okay. Rounding it off, 15.6 kilocalories. And so that completes chapter 1.